Okay, moving on to chapter 8. Um, I'm not going to lie to you. Chapter 8 tends to be among the more difficult material that we cover in this class. It's just been my experience that students find this material particularly challenging. So I've tried a couple of different approaches to teaching this section, and I'm going to try yet again something new here with covering the stuff in chapter 8. What I want to do is I'm just going to start off by giving you the result. I'm just going to tell you exactly how to solve the problems that we're interested in solving in chapter 8. And then when I'm finished doing that, then we'll go back and we'll discuss, why we're interested in solving these kinds of problems and how we know that this is an appropriate way to solve them. So I promise you that explanations will come if you're one of those types of people who needs to know why this works, right? I promise you that I'll explain all of that. But for now, I'm just going to explain how to do it, and then I'll explain why it works and why we care, okay? So first of all, the sampling distribution of the sample mean is the probability distribution of all the possible values of the sample mean x bar. This is a difficult concept to wrap your brain around, but here's an example, right? So let's say the government wants to determine the mean of all US household incomes. So they survey a sample of US households. Now, not everyone in the population gets surveyed. So different samples are going to have different means, right? Like if they went out and they collected one sample of, I don't know, 100,000 individuals, they might find that sample has a sample mean of $67,976. But if they went out and collected a different sample of 100,000 people, then they might find that sample mean is $67,731, right? And so forth, right? Every different sample that they collect is likely to have a different sample mean. And since the sample mean is different from one sample to the next, we can think of the sample mean as a random variable. Okay, which means x bar, right? X bar, the sample mean, is going to take on different values with different degrees of probability. So if we were to somehow list out all of the possible sample means together with the probability that x bar is that value, that would be the probability distribution of the possible values of x bar, and we call that the sampling distribution of the sample mean. So here's what we know about the sampling distribution of the sample mean. And these are the facts that I told you. I'm going to give you them without justification for now, but I promise you I'll explain where these come from in a second, okay? But these are the results, okay? So suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. Then the sampling distribution of the sample mean has a mean of the symbol that we use for the mean of the sample means is mu sub x bar. And it turns out that mu sub x bar is just exactly the same thing as the population mean. So in other words, if you were to list out all of the possible different sample means, all of the different possible x bar values, and then if you took the average of those averages, what you would discover is that the average of those averages is equal to the population mean that you started out with to begin with, okay? So that's the mean of the sample means. The standard deviation of the sample means, now that turns out to be the same as the population standard deviation divided by the square root of the sample size, okay? So again, if you listed out all of the possible different x bars, all of the possible different sample means, and you took their average, right? So if you looked at the average of all the sample means, you would get the population mean. And if you looked at the standard deviation of the sample means, you would get the population standard deviation divided by the square root of the sample size that was used. Okay. So those two pieces of information are important. And now here are two more pieces of information that are important. If the underlying distribution is normally distributed, then the distribution of the sample means is also going to be normally distributed. So again, if you were to make a histogram, so if you were to collect all of the possible different sample means and then make a histogram out of those sample means, it would have a bell shape. All of the different sample means, they would form a bell-shaped distribution. They're normally distributed. So that's if the underlying population is normally distributed. But there's this fact, this really important fact in statistics called the central limit theorem, which says that actually it doesn't matter what the shape of the underlying population is, right? Regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size n increases. And in particular, we usually take the convention that as long as n is at least 30, so as long as your sample size is at least 30, then the distribution of the sample means is going to be normally distributed. The reason that it's important to know that these things are normally distributed is that if we want to compute a probability involving a sample mean of multiple observations, then we can use the normal calculator because we know that the sample means are normally distributed. So we can use the normal calculator. And when we use the normal calculator, you know, we go stat, calculator's normal, and then when we get there, we have to enter some value for the mean and some value for the standard deviation. These are the values that we're going to enter for the mean and for the standard deviation, okay? So if we want to compute a probability involving just a single observation of a normal variable, then we use the normal calculator with the values for mu and sigma given in the problem, just like we did in chapter 7.2. But if we want to compute a probability involving a sample mean of multiple observations, then we can still use the normal calculator, but we would use sigma divided by the square root of n for the standard deviation. So let me give you an example. Actually, I'm going to give you several examples. So this one says the heights of women are normally distributed with mu equals 63.6 inches and sigma equals 2.3 inches. And part A asks, if a woman is randomly selected, or if a woman is selected at random, what is the probability that her height is more than 64 inches? Well, we know that the heights of women are normally distributed. So we can use the normal calculator to compute this probability. Normal. Okay. When we do, we're going to be prompted to enter something for the mean and something for the standard deviation. Now, since this is just a single observation, we're just talking about if one woman were selected at random, right? What's the probability that her height's more than 64 inches? So we're only talking about a probability involving a single observation. And so for the mean, we're just going to put in the value for mu, 63.6 that was given, and the value for sigma that was given, 2.3, okay? And then we're going to look for probability that her height, x, is more than 64 inches. So this is the probability that we're interested in. Let's go to StatCrunch and see what we get. Go ahead, give the video a pause and open up StatCrunch if you haven't done so already. Okay, but in StatCrunch, I'm going to go to Stat, Calculators, Normal. And I'm going to put in 63.6 for the mean and 2.3 for the standard deviation. And then I'm looking for the probability that x is greater than or equal to 64. Okay, and that's that, right? There's nothing new about this particular problem. Oh, the rounding is kind of interesting though, right? The 9 has no place to go, so it has to go up to the 10. So we're going to say 0.4310 when we round to 4 decimal places. Okay, so this is about 0.4310. Okay, so that's nothing new. This is a problem that we knew how to solve back in 7.2. Okay, nothing new there. But now look at part B. Part B says, if 10 women are randomly selected, what is the probability that their mean height is more than 64 inches? Okay, do you see the difference here? It's like instead of looking for the probability of just a single observation, we're looking for the probability that a sample mean of 10 observations falls within a certain that we can still use the normal calculator to compute this probability, but these are the values that we have to enter for the mean and the standard deviation. Okay. So I'm still going to go, so this is a problem. Calculators, normal. For the mean, right, the mean of the sample means, mu sub x bar, is exactly the same thing as the population mean, mu, which is 63.6. Okay, so that's the same as the previous problem. But the standard deviation of the sample means, that's equal to the population standard deviation divided by the square root of the sample size. Okay, so that's going to be 2.3, right? 2.3 divided by the square root of n, right? 10 women in this particular sample. So divide by the square root of 10. So let's see about how much that is. So that's about 0. We'll go 2 decimal places, 0.73. Okay. I rounded to 2 decimal places here because this was rounded to 1 decimal place. So I'm just going 1 decimal place further than the parameters I was given, which is more or less standard practice in this particular textbook. Okay, but that's the only difference between these two problems. So now I'm looking for the probability that a sample mean, right, x bar, is greater than 64. Okay, and the only difference between how I do this problem and how I do this problem is that on this problem, I divided the standard deviation by the square root of the sample size. That's the only difference. So let's go to StatCrunch and see what that does to our probability. Okay, so I'm going to change the standard deviation from 2.3 to 0.73. And then I'm still looking for the probability, in this case, the probability that x bar is greater than or equal to 64, right? So hit compute, and it decreased, right? So I got 0.2919. You can hear my dog going crazy. Somebody just rang the doorbell. Anyway, so that's that. Now, hopefully this makes sense, right? Because we know that the sample mean is 63.6. So the probability that this particular woman is more than 64 inches tall is, pretty likely, because 64 is close to the sample mean anyway. So it wouldn't be unlikely at all for this woman to be 64 inches tall. But if you went out and you collected a sample of 10 women, then the probability that their sample mean is more than 64 inches, now that's going to be a little bit less likely, because the population mean is 63.6. It's like the more women we add into our sample, another way to think about that is that here our sample size was 1, and here our sample size was 10, right? And the more women we add to our sample, the less and less likely it's going to be that our sample mean differs from what the true population mean is. So it makes sense that this probability decreased in this case. It's not always going to decrease, but in this case, it makes sense that it did decrease. Okay, so hopefully that makes some sense to you. Let me give you another example of this. So number 2 here says, a good poker player is expected to earn $1 per hand on average. The standard deviation is approximately $32. I think this is referring to like a specific game, right? So obviously they're not going to earn $1 per hand if you're not playing for money, right? But then I guess it wouldn't really be poker, probably. Anyway, but the point is, in this particular game of poker, a good player is expected to earn $1 per hand on average. So that's our population mean, right? So that's our population mean, mu equals 1. And then it says the standard deviation is approximately 32, so that's our standard deviation, sigma equals 32. Now, part A says, what is the probability that a good poker player earns a profit after playing one hand? Okay, so after playing one hand, our sample size is 1, right? So we're looking for the probability that they earn a profit after one hand, and this is just a probability involving a single observation. So this is, again, this is like a 7.2 problem. Okay, we're going to go to stat, calculators, normal. We're going to, for the mean, we're going to put in 1. For the standard deviation, we're going to put in 32. And then we're looking for what's the probability that they earn a profit. Well, earning a profit just means that their earnings are more than 0, right? So if they earned a profit, then their earnings are more than 0. Okay. So what's the probability that their earnings are more than 0 after one hand? So we'll go to StatCrunch and see about how much that is. So I'm still using the normal calculator. The mean should be 1. The standard deviation should be 32. And we're looking for the probability x is greater than 0. So pretty good odds, right? Pretty good odds that after their first hand, they're going to earn a profit, right, after their first hand. So 0.5124. A little better than a 50% chance, right? Okay, now part B says, what is the probability a good poker player earns a profit after playing 50 hands? Okay, this is an 8.1 problem, right? Because now we're talking about a sample mean of 50 hands. We want their average earnings to be greater than 0, right? We want their average earnings to be a positive number after 50 hands, right? So again, we can use the normal calculator. This time for the mean, we're going to use the mean of the sample means, mu sub x bar. Turns out that that's the same thing as the population mean. Okay, so that's just equal to 1. For the standard deviation, on the other hand, standard deviation of the sample means is equal to the population standard deviation divided by square root of the sample size. So in this case, that would be 32 divided by the square root of 50. Okay. Let's see how much that is. So 32 divided by square root of 50 is about 4.5. And now we're looking for the probability that their average earnings after their 50 hands is more than 0. Let's see what we get. Maybe it would be a good idea to pause and ask yourself, do you think this probability is going to increase or decrease? Okay, so if this is the probability that they're sort of ahead after one hand, then what's the probability that they're ahead after 50 hands? Is that going to increase or decrease based on the fact that they're expected to earn $1 per hand on average? So give the video a pause and see if you can reason out the answer to that question. But here we go. So again, the mean is 1. This time the standard deviation decreases to 4.5. And we're looking for the probability, again, that x bar is greater than 0. Okay, so this time we got 0.5879. 0.5879. 0.5879. Okay, so this time the probability increased, right? And that should make sense. It's like if a good poker player is expected to earn $1 per hand on average, well, they might lose their first game, right? Like there's a pretty good chance they're going to lose their first game. But if they play 50 games, if they're expected to earn $1 per hand on average, then definitely after 50 games, you really start to expect them to be ahead, to have made some kind of profit, right? The probability really didn't increase that much, I guess, from what it was in part A. Let's look at part C now. It says, what's the probability a good poker player earns a profit after playing 100 hands? Same problem, right? Same problem. Stat, calc, norm. For the mean, we're going to put in 1. For the standard deviation, well, go ahead and pause the video. See if you know what you should put in for the standard deviation here. Okay, so for the standard deviation, you should be putting in 32 divided by the square root of 100, because now we're talking about after 100 hands, right? 32 divided by square root of 100. Well, this is exactly 3.2, right? This is exactly, so not approximately, it's exactly equal to 3.2. Okay, let's see what we get. Oh, we're still looking for the same thing though. Probability x bar is greater than 0. Let's see what we get. Okay, so another increase, right? Of course, makes sense, right? After 100 hands, we definitely start to suspect they're going to be ahead. So that's 0.6226. Oh no, 0.6227. Now, I think you've got the idea. And so just going back here, you can play around with all kinds of scenarios like, well, what's the probability that they're ahead after 1,000 hands, right? Like if they played 1,000 hands. For the standard deviation, we would put in 32 divided by square root of 1,000. And we would, the standard deviation would be like 1.0, I guess just 1.0 is what we would put in. So after 1,000 hands, there's like an 84% chance that they're going to be ahead, right? What about after like 5,000 hands? Then we would divide 32 divided by square root of 5,000, and the standard deviation there drops to 0.45. So after 5,000 hands, they're almost certain. They're almost certain to have made a profit after playing 5,000 hands. Of course, this is for a good poker player, right? These are for good poker players. Generally speaking, gambling is a bad idea. Gambling is always a bad idea in the long run if you're talking about games that are pure chance. And definitely if you're a bad poker player, then it's still quite a risky endeavor, right? But assuming that you're a good poker player, after 5,000 hands, you're almost certain to be ahead. There's like a 98% chance you're going to be ahead. Okay, so that's that. Let me give you one more example related to this poker scenario. It says, what is the probability a good poker player loses $100 after playing 25 hands? Ooh. So if they're expected to win $1 for each hand they play, then after 25 hands, you kind of expect them to have earned a profit of $25. But this question is asking, what's the probability that they've lost $100 at the end of 25 hands? Well, again, we're going to go stat, calculator, normal. Again, we're going to put in 1 for the mean. And for the standard deviation, we're going to put in sigma divided by square root of, or not sigma, I guess it would be, what was sigma? 32, right? So we put in 32 divided by the square root of 25 this time, 25. Oh, 32 divided by 5. That's exactly 6.4. So this comes out to exactly 6.4. Now, figuring out what probability to compute is a little tricky here. We want to know what's the probability that they lose $100. So if they lose $100 in total, then that means on average for the 25 games that they played, they lost $4 on each hand. So we want to look for the probability that X bar is less than or equal to -4, right? In other words, if their average loss on each hand is -$4, then after 25 hands, right, 4 times 25 is 100. So after 25 hands, they've lost $100, which is the probability we're looking for. Okay, so we want, what's the probability their average loss is $4? Okay, so let's go to StatCrunch and see what we get. So the standard deviation we said would be 6.4 this time, and we're looking for the probability that they lose $4 for each hand on average. Okay, so that comes out to about 0.2173. Okay, so 0.2173. Okay, so that's the idea there. That's really the main moral of the story in this section, is that if you want to compute a probability involving a sample mean, then you can still use the normal calculator. You just have to adjust what you enter in for the standard deviation. Okay. Another type of problem that you might encounter in the homework would be something like this. It says the mean speed limit in Montana is 54 miles per hour with a standard deviation of 12 miles per hour. Describe the sampling distribution of the sample mean for a sample of 40 roads in Montana. Okay. When they ask you to describe the sampling distribution of the sample mean, what they're asking you to do is to describe what is the shape of the distribution, what is the center of the distribution, and what is the spread of the distribution. And for each of those things, we have a result which we've already covered on the previous page, right? The shape of the distribution is going to be normally distributed, right? The shape becomes approximately normal as n increases, and in particular, right, if n is bigger than 30, bigger than or equal to 30, right? So the distribution is approximately normal as long as n is greater than or equal to 30. So that takes care of the shape. This is the center of the distribution, and this is the spread of the distribution. Okay, so to answer number 3 here, we would say, all right, so the shape of the distribution. Our sample size here is 40. So we say something like, since n equals 40 is greater than 30, we'll say the sampling distribution of X bar is normal, right? It's normally distributed. Normally distributed. Right? Or in other words, that's like a fancy way of saying it's bell-shaped, right? If you were to look at a histogram of all of the possible sample means, that histogram would be bell-shaped, right? It's bell-shaped. Okay, so that's the shape. The center of the distribution, the center is the mean of the sample means, right? So again, if you made a distribution of all the possible sample means, what's the average of those sample means? What's the mean of the sample means? Well, it's going to be the same as the population mean. And the population mean, we're told, is 54 miles per hour. So there's the center of the distribution. And then the spread of the distribution is going to be sigma sub X bar, right? So you make a distribution with all of the possible values of X bar, and then you take the standard deviation of those, and that's going to be equal to the population standard deviation divided by the square root of your sample size, which in this case, we were told the standard deviation was 12, and the sample size was 40, right? 40. So 12 divided by square root of 40 is approximately, let's go one decimal place. So this is approximately 1.9. So there's the spread, right? That's what they mean when they ask you to describe the sampling distribution of the sample mean. They want you to describe the shape, center, and spread. And that's all there is to it. Now you may wonder, well, what if your sample size is not greater than 30? What if it's less than 30? Well, the shape of X bar is still going to be normally distributed if the underlying population is normally distributed. Now, if the underlying population is not normally distributed, if it's, say, skewed left, and your sample size is only like 12 or something, well, then you don't know what the shape of the distribution is, right? There's not enough information to be able to answer this question. You'd have to actually look at the raw data to work that out, okay? So that's that. But the center and spread are still going to follow this. Regardless of the shape of the underlying population, the center and spread are still going to be given by these little formulas. So that is the moral of the story. I almost hesitate to say this, but you could almost stop watching the video now and you could probably answer all of the homework questions just fine, okay? But if you want to have a deeper understanding of what it is that we're talking about, then keep watching, okay? Like if you want to know where the formulas came from, keep watching, okay? So on the surface, these are not difficult problems, right? But the more you think about it, the more you're like, what in the world did we just do, right? It's a very meta concept. We're not talking about the probability of one event. We're talking about the probability of the sample mean of multiple events. Is it really as easy as just dividing sigma by the square root of n? And how do we know this, right? How do we know that that's really as easy as it is? Like, are we even justified in using the normal calculator for this, right? Like, how do we understand this? How do we know that this is true? So what I want to do in this example, I want to build a sampling distribution by hand. And then after that, we'll look at some simulations in StatCrunch because it'll be easier to look at the simulations in StatCrunch. And hopefully what that will give you is some understanding of how we know that the sample mean really is normally distributed, and how we know that the mean of the sample means is really equal to the population mean, that the standard deviation of the sample means is really equal to the population standard deviation divided by square root of sample size. All right, so let's look at some examples. This one says, James, Lori, Kate, and Clint live together in a household, and they share a data plan through their cell phone company, which charges by the gig. The chart below summarizes the number of gigs each member of the household uses per month. What is the population mean, mu? So that's easy, right? This particular household only has these 4 individuals in it. So this is the entire population. The population mean is just going to be 2.4 plus 3.2 plus 2.5 plus 1.7 divided by 4. Okay. So that's easy enough. Let's see what we get. So I'm getting 2.45. Okay, so there's the population mean. Now part B says, write down all samples of size 2 and compute their means. Okay, so one possible sample of size 2 would be James and Lori. I'm just going to abbreviate, James and Lori. Another possible sample of size 2 would be James and Kate. Another possible sample of size 2 would be James and Clint. Oh, I better write these closer together or I'm going to run out of space. James and Clint. Okay, another possibility would be Lori and Kate. Lori and Clint. And then Kate and Clint. Okay, so those are all of the possible samples of size 2. Now let's compute their sample means, okay? So for James and Lori, I'm not going to show all the work because I don't have enough space to do that. I'm just going to use my calculator. But for James and Lori, we would say, you know, the sample mean is going to be 2.4 plus 3.2 divided by 2. All right, so 2.8. For James and Kate, same deal, right? We're going to say 2.4 plus 2.5 divided by 2, and that equals 2.45. So I'll let you go ahead and work out the rest of them. I'll race you. Okay, so there are all the sample means. If you're not ready to move on, pause the video and finish writing this stuff down. I'm going to move on now. Part C says, construct the sampling distribution of the sample mean. The sampling distribution of the sample mean is going to list off all of the possible values of x bar together with the probability that x bar takes on that value, right? So what are the possible, let's see if we can list them in order. So I think the smallest one is 2.05. And then we have 2.1. And then we have 2.45. And then we have a 2.8. And we have a 2.85. So these are all of the possible values of x bar, but they're not all equally likely to occur, right? Like the probability that x bar is 2.05, well, there was only one time that that happened out of our 6 possible samples, right? So that's just a 1/6 probability of occurring. Probability x bar is 2.1, again, 1/6. The probability x bar is 2.45, now that's 2/6, right? Because that happened twice, right? So 2/6. Or in other words, 1/3. Probability x bar is 2.8, 1/6, 2.85, 1/6. And this is a probability distribution, right? Like if you add these up, you get 6 out of 6, which equals 1. Now part D says, what is the mean of the means? Mu sub x bar. So the mean of the means, mu sub x bar. Well, so we would add up all of the sample means and divide by the number of sample means, which is 6. So we're going to say it's 2.8 plus 2.45 plus 2.45. Or sorry, 2.05. 2.8 plus 2.45 plus 2.05. I was getting ahead of myself. Plus 2.85 plus 2.45 plus 2.1 divided by 6. Let's see what we get. That comes out to 2.45. Ah, interesting, right? Because 2.45 was the population mean. So there's that relationship, right? We said that the mean of the sample means, mu sub x bar, is going to be equal to the population mean, mu. And here we've just done an example that that proves it, at least for this particular case. But I promise you that it is true in general, right? This is always true. Now, we weren't asked to do this, but we could look at the standard deviation of the sample means. We could get that pretty easily if we just inputted these into StatCrunch and then computed the standard deviation. I'm not going to do that, but if we were to do that, we would find that we would get the same standard deviation as the population standard deviation divided by the square root of n. Okay, I'm not going to walk you through that because I do want to go to StatCrunch and run some simulations, which will give us some even better examples because they're going to give us some visuals to look at as well, so that we can also talk about the shape of the distribution. This one says scores on an IQ test are normally distributed with a mean score of 100 and a standard deviation of 15. What is the shape, center, and spread of the sampling distribution of the sample mean for a sample of size 9 and then for a sample of size 25? So So I'm going to go to StatCrunch now to do this. So to do this, now we have, let me take you back for a second. We have formulas, right? We have formulas that allow you to say what the shape, center, and spread of these distributions are going to be. However, what I want to do is run the actual simulation in StatCrunch to prove to you, or to try to at least build up evidence to convince you that the formulas that we have are correct. When you're actually going through the homework, you shouldn't run simulations to answer the questions in the homework. Just do what we did on number 3. If you were confronted with a problem like this, just do what we did on number 3, okay? But the purpose of this exercise is just to convince you that those formulas actually work. And I'm going to convince you of it by looking at some simulations. So again, going to StatCrunch. To run this simulation, you don't have to follow along. You can just watch what I'm doing. If you want to follow along, you can. But I'm going to go to Applets, and I always have to remember I always have to try to recall how this works. Anyway, we go to Applets and then sampling distributions. And I want a bell-shaped distribution to start with, because the problem says, right? The problem says that that IQ tests IQ scores are normally distributed, right? So I'm going to start with a normal distribution, in other words, a bell-shaped distribution. It says that they're normally distributed with a mean of 100 and a standard deviation of 15. So I'm going to do that to set up my simulation. And I want to simulate collecting a bunch of samples of size. In part A, I want the sample sizes to be 9. So if I come up here and click on one time, what it's going to do is it's going to simulate, it's just going to randomly select a sample of size 9. And if you are following along and doing this yourself, you're likely to get a different sample than the one that I'm coming up with. But what it's going to do is it's going to it's going to randomly choose individuals from this population, and it's going to compute their sample mean, and it's going to drop their sample mean right here. And so let me do that. Right, so it's simulating the collection of a sample of size 9, and then it computes their sample mean, right? So it computes their sample mean, puts it right there. I could do this again, and a different sample is going to produce a different sample mean, right? Different sample is going to produce a different sample mean. So I could keep doing this over and over and over again, but I'm just going to click on 1,000 times at this point, right? So if I click on 1,000 times, it's like they've taken 1,000 samples of size 9. And after taking 1,000 samples of size 9, look at this distribution, right? These are all the sample means. These are all the individual sample means, and they've been kind of stacked on top of one another. And you can see that they make a bell-shaped distribution. In fact, you can keep collecting samples of size 9, but the shape of the distribution is bell-shaped. Now, over here you can see the mean of these sample means, right? So here, this mean is just taking the sample mean of this last sample that was collected, but this is taking the average of all of the sample means in this distribution, right? And what you'll notice is that the mean of those sample means is equal to the population mean that we started with. I mean, not exactly, but it's pretty close, right, to the population mean that we started with. Now, the standard deviation is about 5. That's interesting, right? Because we said that the standard deviation of the sample means would be the population standard deviation divided by the square root of the sample size, right? Well, 15 divided by the square root of 9, right? Square root of 9 is 3. 15 divided by 3 is 5, right? Sure enough. Okay. So there's that one, right? Let me reset this now. Part B wants us to do this for a sample of size 25. So I'm going to change the sample size to 25. So if I collect one sample of size 25, there's the sample mean. I could do this again and again and again, right? And you see that you get this distribution starts popping up. If I just do this 1,000 times, right, then I get this distribution. Once again, a bell-shaped distribution. Once again, the mean of the sample means is pretty much the population mean. And then once again, the standard deviation of the sample means is the population standard deviation, 15, divided by the square root of the sample size, 5, right? 15 divided by 5 is 3. Okay? So that's what happens if we're starting with a population that's already normally distributed. But what if the population that we're starting with is not normally distributed, right? So let's run another simulation. And this time, instead of choosing a bell-shaped distribution, let's choose a right skewed distribution. Okay, so I'm getting this different kind of simulation. And the instructions say to collect samples of size 4 in part A and then size 49 in part B. So if I collect one sample of size 4, there's the sample mean. If I do it again, there's a different sample mean and a different one and a different one. If I did it 1,000 times, this is the distribution I would end up with after 1,000 iterations, right? You can see that this is not quite bell-shaped. It's a little bit skewed right, okay? It's not as badly skewed right as the population data that we started with, but it is still skewed right? You've got this little tail out here. And the more samples you collect, the more you can kind of see the tail start to creep up, right? So you've got this skewed right distribution. So the shape of the distribution is skewed right. But the mean of the distribution, the mean of the sample means, is close to the population mean. The standard deviation of the sample means is the population standard deviation, right? 12 divided by square root of sample size 2, right? 12 divided by 2 is 6, okay? I'm rounding, of course. Okay, so the shape is skewed right, but the center is still mu, and the standard deviation is still sigma divided by square root of n. So let me reset this now, and let's simulate taking samples of size 25 instead. Or no, 49, I'm sorry, 49. In part B, we wanted to do samples of size 49. So if I take one sample of size 49, there's the sample mean I get. I could do it again and again. Okay, if I did it 1,000 times, then I end up with that. Notice the shape of that distribution. Okay, this isn't skewed right anymore. This is bell-shaped. Okay, when our sample size got larger, the mean or the distribution of the sample means became bell-shaped. That's what the central limit theorem says. That's what the central limit theorem says will happen. And that's why we're justified to go ahead and use the normal calculator when we're computing probabilities involving sample means, as long as our sample size is large enough. And again, the cutoff value that we usually use is 30, right? So as long as your sample size is at least 30, then you can safely conclude that the distribution of your sample means is going to be bell-shaped. Okay? So hopefully those simulations kind of convince you that the facts that I gave you on page 1 are actually true, right? These are actually true facts. And again, that's the purpose of looking at these simulations. But when you actually go to do the homework problems and you want to describe the sampling distribution of something, just do it the way that we did exercise 3, because now you know that these formulas really do work. And so you can just use the formulas instead of running a simulation. Okay. We have some blanks to fill in. I'm not going to fill in anything here, right? We just kind of discussed it. We discussed these things as well. It says exactly how large does n need to be in order for x bar to be normally distributed? Well, that depends on how badly skewed the population data is. But as a general rule of thumb, we'll say that X bar is normally distributed if one of the following are met. If either the population is normally distributed or if the sample size is at least 30. Okay. If at least one of those criteria is met, then we're safe to conclude that X bar is normally distributed. Now, I want to end this discussion by talking about why we care about problems like this. Okay, why do we care about being able to compute the probability that a sample mean is within a particular range? Well, it turns out that this is exactly the kind of probability that we need in order to be able to in order to be able to draw inference from data. Okay, and let me explain why. So, let's say that we want to test if a fertilizer causes corn stalks to grow taller. So we need to go out and test that, right? To test to see if that's true. So what we might do is we might apply the fertilizer to a plot of corn stalks, wait a few months, and then measure the heights of those plants, right? Now, in order to determine if the fertilizer is effective, we would then want to compare the average heights of our corn stalks, our fertilized corn stalks, with the average heights of just corn stalks in general. And if the average height of our plants is significantly more than the average height of corn stalks in general, then we have evidence that the fertilizer would make any corn stalk of the same species grow taller, right? But what exactly do we mean by significantly more? Like, let's say that the average corn stalk is, 12 feet tall, and our fertilizer makes corn stalks grow to be 12.1 feet tall, right? Is that good evidence that our fertilizer is effective? Or could it just be a fluke? Could it just be that, that particular year, the conditions were just right to make the corn grow a little bit taller than average or whatever, right? Like what do we mean exactly by significantly more? Is there a way to be mathematically precise about it? And the answer is yes. Right? One thing that we could do would be to assume that the fertilizer has no effect, and then compute the probability that we would get a sample of corn plants whose sample mean is as large as ours. In other words, we would compute the probability that X bar is greater than or equal to the sample mean that we got, given that the fertilizer is ineffective. Okay? If this probability is really small, then that tells us that this assumption is probably wrong. And then we would have evidence to support the claim that the fertilizer actually is effective. Okay? Notice that this probability is a probability involving X bar. Okay? So these are exactly the kinds of probabilities that we need to be able to compute in order to be able to perform inference. So let me just give you one last example where we're actually going to perform a little bit of inference here. It says corn stalks are 13 feet tall on average with a standard deviation of 2 feet. A fertilizer is applied to a field, and the 2,000 corn stalks that are grown on that field end up having an average height of 13.5 feet. Does this provide good evidence that the fertilizer is effective? Let's see. Our corn plants are half a foot taller than the average corn plant. Is that good enough to say that the fertilizer actually works? The only way to be mathematically sure about that is to compute the probability, right? So we're going to compute probability that X bar is greater than or equal to the sample mean that we got, 13.5, given that the fertilizer is ineffective. If the fertilizer is ineffective, then really the population mean would be 13. And the standard deviation would be 2, right? Because those are the values that we were given, right? So to compute this probability, right, we're going to go stat, calculators, normal. We're justified to use the normal calculator because our sample size is 2,000, right? That's way bigger than 30. So we're justified in using the normal calculator. We go stat, calculators, normal, and we're going to put in for the mean 13, for the standard deviation 2, and then we're going to look for probability X bar is greater than or equal to 13.5. Let's see what we get. I'm kind of excited because I haven't done this example before. I'm curious to know. We're going to go stat, calculator is normal. mean is 13, standard deviation is 2. So looking for probability x bar is greater than or equal to 13.5. Okay, so 0.4013 is that probability. Okay, so in other words, there's like a 40% chance that even if the fertilizer is ineffective, we would still get our corn stalks to be 13.5 feet. If there's a 40% chance that this would just happen just by chance, then the fact that it happened doesn't really tell us much, right? It doesn't really tell us that the fertilizer is effective, okay? So the answer is, so does this provide good evidence that the fertilizer is effective? No. No, we could easily have gotten corn, an average height of 13.5 feet just by sheer chance, right? In fact, there's a 40.13% chance of this happening. Okay, so in fact, there's a 40.13% chance of this happening. If the probability we had gotten here had been something really small, though, like if we had gotten probability x bar is greater than 13.5 to be approximately, 0.001 or something like that, then what that would tell us is that there's like a 0.001 probability that we would get this result if the fertilizer were ineffective. And since that's a really, really small probability, the fact that it did happen tells us that probably it was the fertilizer that caused it to happen. And so then we would have evidence that the fertilizer is effective. This is the basis of all of the inference that we're going to be performing in Unit 3. Okay, and basically what this probability is called is the p-value. This is the p-value of the hypothesis test that we would be running. And so we will talk about all of this stuff in more detail in the next unit. But that is why we're interested in computing probabilities involving x bar. So hopefully that all made sense to you. As far as actually finishing the homework problems, for the most part, right, if you just follow along with what we did on the first couple of pages, you should be golden.